In this video, we're going to focus on finding the linearization of a function and how to estimate a value using that function. We're also going to talk about differentials, dx, dy, and we'll work on a few problems relating to that as well. So let's say if you want to calculate the square root of 3.99 or the square root of 37. Now you know the square root of 3.99 is close to the square root of 4, which is 2. But we don't know what the exact number is. But nevertheless, we can get a good approximation of it. And the square root of 37, we know it's just above 6, because the square root of 36 is 6. So we can use linearization to get a good estimate of the square root of 37. Now let's talk about how it works. So let's say if we have a function, let's say this is f of x, and we want to find the linearization at some point a. So the y value that corresponds to that particular x value is f of a. The linearization is basically the tangent line function at that point. So as you can see, if you want to estimate, let's say, f of b, you can use the tangent line to find f of b, because the tangent line is very close to the function at anywhere close to point A. So a tangent line is a good approximation of the actual function when it's very close to the point of interest. As you move further away, let's say at some point C, the y value of the tangent line becomes significantly different from the y value of the f of x function. So linearization works when you're very close to the point of interest. So how do we go about finding the linearization of a function? It's the same way as finding the tangent line of an equation. Whenever you want to find the equation of a tangent line, you can use the point-slope formula. Y minus y1 is equal to the slope times x minus x1. So the point is x1 comma y1. x1 is basically a, and y1 is the y value at that x value. So that's f of a. Y is equal to f of x, or in this case, L of x, which we'll call the linearization function. And the slope is you can find it from the derivative. So it's really f prime of a. It's the slope of the tangent line at point A. And the only thing that we're missing is, I believe that's it. That's all we need. So let's replace y with L of x. y1 is going to be f of a. And that's equal to the slope, which is, let's make some space. The slope we said is f prime of a times x minus a. So that's the linearization function. To make sure you realize that the slope is f prime of a is basically x1, and y1 is f of a. So L of x is equal to f of a plus f prime of a times x minus a. Let's try a practice problem. Let's say if you have a problem that states find the linearization L of x of the function at a. And let's say that f of x is equal to the square root of x, and a is equal to 36. So how can we find the linearization L of x and use it to estimate the square root of 37, which is f of 37? So let's write the formula first. So we know that L of x is equal to f of a plus f prime of a times x minus a. So let's evaluate each one first. Let's find the first derivative. So what is f prime of x? Well, we can rewrite f of x. The square root of x is x to the 1/2. So f prime of x, using the power rule, is going to be 1/2 x to the minus 1/2. 1/2 minus 1 is negative 1/2. And then we could rewrite it like this: 1 over 2x to the 1/2. Whenever you move a variable like x from the numerator to the denominator, the exponent will change from negative 1/2 to positive 1/2. And then we could convert it back to radical form. So it's 1 over 2 radical x. So if that's f prime of x, then f prime of a, where a is 36, is going to be 1 over 2 times the square root of 36. And the square root of 36 is 6. And 2 times 6 is 12. So therefore, f prime of a is 1 over 12. Now what about f of a? We know that f of x is equal to the square root of x. So therefore, f of a, or f of 36, is equal to the square root of 36, which is 6. So let's replace f of a with 6. And this is going to be x minus a, or minus 36. And this is equal to L of x. So now let's simplify the function. So let's distribute 1 over 12 to x and negative 36. So it's 1 over 12 times x. Negative 36 divided by 12 is negative 3. And 6 minus 3 is 3. So the linearization is 1 over 12x plus 3. So now let's use this function to estimate f of 37. So L of 37 is the linear approximation of y when x is 37. So this is going to be 37 divided by 12 plus 3. So this is about 6.083. Now the 3 continues to repeat, by the way. Now what is the exact answer? What is f of 37? The square root of 37 is 6.08276. So as you can see, 6.083 is a good approximation of the square root of 37, which is, if you round it, 6.083. Now it's your turn. Let's say that f of x is equal to x cubed and a is equal to 2. Using this information, go ahead and find the linearization L of x of the function at a and use it to estimate f of 2.1. So basically, estimate 2.1 raised to the third power. Now let's see if we can estimate it without a calculator, and then we'll check the actual answer with a calculator, because sometimes you may not be allowed to use a calculator. So let's go ahead and begin. Let's write the linearization function. So we know that L of x is equal to f of a plus f prime of a times x minus a. So let's find the first derivative. F prime of x is the derivative of x cubed. Using the power rule, it's going to be 3x squared. So therefore, f prime of 2 is 3 times 2 squared. 2 squared is 2 times 2, which is 4 times 3, that's 12. Now we need to find f of a, which is f of 2, and 2 to the third power is 8. So f of a is 8, and f prime of a is 12. So now we can write the L of x function. So this is equal to 8 plus 12 times x minus 2. Now let's distribute the 12. So it's 12x, and 12 times negative 2 is negative 24. 8 minus 24 is negative 16. So L of x is 12x minus 16. Now that we have the L of x function, let's use it to estimate f of 2.1. So let's find L of 2.1 first. So 12 times 2.1 minus 16. So how can we do this without a calculator? 2.1 is basically 2 plus 0.1. So let's use the distributive property. 12 times 2 is 24. And what's 12 times 0.1? Whenever you multiply something by 0.1, all you need to do is move the decimal 1 unit to the left. So 12 times 0.1 is 1.2. And 24 minus 16 is 8. So this is going to be 8 plus 1.2, which is 9.2. So L of 2.1 is 9.2. So therefore, we could say that 2.1 to the third power is approximately equal to 9.2. Now let's see if our approximation is very close to the actual answer. So let's type in 2.1 raised to the third power in the calculator. The exact answer is 9.261. So it's not too far away, but if you round it, this would round to 9.3, and this is about 9.2. As you can see, 2.1 is not too close to 2. So therefore, there's going to be some error, but we still have a decent approximation. Let's say if you're doing your calculus homework and you see a problem that says estimate the given number using a local linear approximation or using differentials. And let's say it's the cube root of 8.1. How would you do that? Now you know the answer is very close to 2 because the cube root of 8 is 2. But is it going to be like 2.1, 1.9, 2.2, 2.05? What is it exactly? Notice that we're not given f of x in this problem, and we're not given the value of a, so we have to find it ourselves. So we could say that a is not exactly 8.1, but it's a number close to it. We know the cube root of 8. The cube root of 8 is exactly 2, so we want to choose our a value to be 8 because we know the value of f of a. F of x is simply the function. Replace 8.1 of x, and then you'll have f of x, which is the cube root of x. So we need to find L of x, which we know it's going to be f of a plus f prime of a times x minus a. So now that we have f of x and a, we can get to work. So let's find the first derivative. So if we rewrite the function, f of x is x to the 1/3. So therefore, using the power rule, f prime of x is 1/3 x to the negative 2/3. 1/3 minus 1 is the same as 1/3 minus 3/3, which is negative 2/3. And if we rewrite it, it's going to be 1/3 x to the positive 2/3. So now what we need to do is plug in a to find f prime of a. So a is 8, so f prime of a is going to be 1/3 times 8 raised to the 2/3. So what is 8 raised to the 2/3? How can we find the value of that? Eight raised to the 2/3 is the same as 8 to the 1/3 squared. 8 to the 1/3 is basically the cube root of 8, which is 2. And 2 squared is 4. So 8 to the 2/3 is 4. So this is going to be 1/3 times 4. which is 1 over 12. So now we have the value of f prime of a. And we know a is 8. Now we need to find f of a. So f of a, or f of 8, is equal to the cube root of 8, which is 2. So now we can find L of x. So L of x is 2 plus, let's distribute 1 over 12 to x and 8. So it's going to be 1 over 12 times x minus 8 over 12. And 8 over 12 reduces to, if you divide both numbers by 4, it's going to be negative 2 over 3. Now we need to get common denominators to add negative 2/3 to 2. So 2 is basically 2 over 1. And if you multiply the top and the bottom by 3, 2 is the same as 6 over 3. So now if we add the 2 together, 6 over 3 plus negative 2/3, which is just 6 over 3 minus 2 over 3. 6 minus 2 is 4. So this is plus 4/3. So this is our L of x function. And now let's use it to approximate the cube root of 8.1. So L of 8.1 is going to be 1 over 12 times 8.1, or 8.1 divided by 12, plus 4 over 3. Now let's see if we can do this without a calculator. Now let's multiply this fraction by 10 over 10. 8.1 times 10 is 81. You just got to move the decimal point 1 unit to the right. And 12 times 10 is 120. So let's go ahead and get common denominators. Let's multiply 4 over 3 by 40 over 40. 40 times 4 is 160, and 3 times 40 is 120. So if we add these two, 160 plus 81 is 241. You can add them like this if you want. 0 and 1 is 1. 6 plus 8 is 14. Carry over the 1. 1 and 1 is 2, so you get 241. So therefore, it's going to be 241 divided by 120. So let's turn that into a decimal. This is a little bit more than 2. 240 over 120 is about 2. But using long division, we can do it this way. 120 goes into 241 2 times. There's a remainder of 1. Now we need to add a 0, so let's add a decimal point. Now 120 goes into 10 0 times. So let's add another 0. 120 goes into 100 0 times. So let's add another 0. How many times does 120 go into 1,000? So it's 120, 240, 360. And if you keep adding 120, it's going to be 480, 600, 720. 840, 960, 1080. So it's 1, 2, 3, 4, 5, 6, 7, 8 times. 8 times 120 is 960. So 1,000 minus 960 is 40. Now let's add another 0. How many times does 120 go into 400? 4 is too much. It exceeds 400, but 3 is less than 400, so it's going to be 3. 120 times 3 is 360. Notice that 400 minus 360 is 40 again, which if you add another 0, it's going to be 400, and 120 goes into 400 three times. And then it's going to be 400 minus 360 again, so it's 2.008333 repeated. So therefore, L of 8.1 is about 2.08333 repeated. Now let's find the exact answer of the cube root of 8.1 using a calculator. So the cube root of 8.1 is the same as 8.1 raised to the 1/3. And the exact answer is about 2.008298885, which rounds to 2.0083. So this is a good approximation for it. For the sake of practice, let's try another problem like that. So use linearization to approximate ln of 1.05. So go ahead and pause the video and work on this example. So we need to know what the function is, f of x, and we need to choose a value of a. So f of x is going to be ln x. Whatever number you see, replace it with x. Now, choose a value of a, ideally an integer, where you know the ln of that value. The best value to choose is 1. 1 is the closest integer to 1.05. And also, ln 1 is 0. So that's the best value to choose for a. So now let's find L of x, which is going to be f of a plus f prime of a times x minus a. So f of a, which is basically f of 1, that's ln 1, and we said ln 1 is 0. Now f prime of x, the derivative of ln x is simply 1 over x. So therefore f prime of a, or f prime of 1, is 1 divided by 1, which is 1. So therefore we know that f of a is 0 and f prime of a is 1. So now we can find L of x. So the L of x function is equal to f of a, or 0, plus f prime of a, which is 1, times x minus a, where a is also 1. So L of x is simply x minus 1. So now let's calculate L of 1.05. So 1.05 minus 1 is simply 0.05. So this is the estimation. Now let's get the exact value. ln 1.05, if we type it in, it's going to be 0.0488, which is approximately 0.05 if you round it. So as you can see, linearization is a very useful technique to approximate certain numbers where you know a known value. So let's say if you know the square root of 9 is 3, you can use local linearization to estimate, let's say, the square root of 9.3 or something, or 9.4. So it's very useful to find a value that is close to a known value. Let's try one more example, but one dealing with a trig function. So let's find tangent 46. Let's approximate it. So we know that f of x has to be tangent x. But what is a? What a value should we choose in this problem? You don't want to choose 47, because do you know what the tangent of 47 is? And let's say this is degrees. The best value to choose that's close to 46 is 45, because tangent of 45 degrees is 1. L of x is going to be equal to f of a plus f prime of a times x minus a. So f of a, or f of 45, is tan 45, which we said is equal to 1. Now we need to find f prime of a. f prime of x, the derivative of tangent x, is secant squared. And so f prime of a, or f prime of 45, is secant squared 45. Now secant is 1 over cosine, so secant squared is 1 over cosine squared 45. And cosine 45, if you're familiar with the unit circle, is the square root of 2 divided by 2, and it's squared. Radical 2 squared is basically root 2 times root 2, which is square root 4, which is 2. And 2 squared is simply 4. 1 divided by 2 over 4 is the same as 4 over 2 if you use the keep, change, flip principle. So this whole thing is equal to 2. So therefore, we could say that f prime of a, or f prime of 45, is equal to 2. So L of x is equal to f of a, which is 1, plus f prime of a, which is 2, times x minus 45 degrees. Now here's a question for you. Should we use degrees or radians? What do you think? Will it work if we use degrees? Well, let's find out. So let's say if a is 45, and if we plug in x as 46, this is going to be 1 plus 2 times 46 minus 45. 46 minus 45 is 1. So then it's 2 times 1, which is 2, plus 1 is 3. If you type in tangent 46 in your calculator, make sure it's in degree mode. Tan 46 is 1.0355. So this is the exact answer. Notice that our answer is not close to it, so therefore we shouldn't use degrees. Let's convert 45 into radians. To convert degrees into radians, multiply it by pi over 180. So if you divide it backwards, 180 divided by 45 is 4, so it's pi over 4. So therefore, L of x, it's going to be f of a, which is 1, plus f prime of a, which is 2, times x minus pi over 4. Now you don't want to plug in 46 degrees. You want to convert degrees into radians. But let's distribute the 2 first. So it's 1 plus 2x minus 2 pi over 4, which reduces to pi over 2. Now 46 degrees multiplied by pi over 180. Let's reduce it. So it's 46 pi over 180. If we divide by 2, it becomes 23 pi over 90, which we can't simplify it any further. So it's 1 plus 2 times 23 pi over 90 minus pi over 2. 90 divided by 2 is 45. So what we now have is 1 plus 23 pi over 45 minus pi over 2. So let's get a common denominator. So let's multiply this one by 45 over 45 and this one by 2 over 2. So it's 1 plus 46 pi over 90 minus 45 pi over 90. 46 minus 45 is 1. So it's 1 plus pi over 90. Okay, I'm definitely using a calculator for this part. So pi divided by 90 is 0.0349 plus 1. So you get 1.03497. Now keep in mind the exact answer of tan 46 is 1.03553. So as you can see, it's a good approximation. So when you're dealing with trig functions, even though you want to estimate tan 46, when you plug into your linearization function, make sure a and x is in radians and not in degrees, because it won't work in degrees. The standard unit for angles is the unit radians. So, just something to know. Now let's move on into differentials. So you know that y is equal to f of x. And if we differentiate both sides with respect to x, the derivative of y is 1 times dy dx. And the derivative of f of x is simply called f prime of x. So if we multiply both sides by dx, these two will cancel, and we can see that the differential y is equal to f prime of x times the differential x. Now you want to save this equation because it's going to be useful. Dx is equal to delta x. Dy is approximately equal to delta y. So what is delta x and what is dx? We know that delta x is simply the change in the x variable. So it's like x2 minus x1. Delta y is the change in the y variable. It's y2 minus y1. You can also view delta y as being f of x plus delta x minus f of x. This is y2 minus y1. Or you can see it this way: f of x2 minus f of x1. Remember, we said that delta x is x2 minus x1. So if you solve for x2, delta x plus x1 is equal to x2. So x2 is basically delta x plus x1. And basically we get what we have here. So this is f of x, or f of x1, and this is f of x plus delta x, or f of x plus delta x plus x1. So that's delta y. It's the change in the y values. Delta x is the change in the x values. So how does all of this relate in linearization? Let's draw a graph. So let's say if we have a function that looks like this. And let's say we want to draw the tangent line at this point. Let's call that point x1. So the y value that corresponds to this point is y1. Now let's choose another point of interest. This is going to be x2. And the y value that corresponds to x2 is y2. So we said that delta x is the difference between x2 and x1. So this is delta x. Delta y is the difference between y2 and y1. So this is delta y. So where is dx and dy? So as you can see, delta x and delta y is associated with the function f of x. Dy and dx is associated with the tangent line. So dx is defined as delta x, which is x2 minus x1. So this is equal to dx. Dy is the difference between y1 and the new y value of the tangent line, which is basically this distance here. This is dy. Notice that delta y and dy are not the same. delta y is greater than dy for this particular function, since the function increases faster than the tangent line. So delta y is greater than dy. Now, if these 2 points are very close, then delta y is approximately equal to dy, but they're not the same. But they can be close to each other. So let me use the approximately equal symbol. So now you see the difference between delta y and dy. So delta y is associated with the change in the y value. It's y2 minus y1, or f of x plus delta x minus f of x, where dy is equal to f prime of x times dx. It's the slope times the differential of x. Now let's work on some problems. So let's say if we have the function y is equal to x to the 6 plus 7x squared plus 3x. Find the differential of the function. So the derivative of y is going to be 1 times dy. Now you can say it's 1 times dy dx and then multiply both sides by dx if you want. But the way I'm going to do this is I'm going to differentiate every variable and add the differential of that variable next to it. So every time I differentiate a y variable, I'm going to add dy to it. So let's say if I'm going to differentiate x cubed, it's going to be 3x squared times dx. If I want to differentiate r to the 4th, it's going to be 4r to the 3rd times dr. So the derivative of x to the 6th is 6x to the 5th. The derivative of 7x squared is 14x. And the derivative of 3x is 3. And all of these will be multiplied by dx. So that's the differential. So therefore dy is equal to everything that we have on the right side. Let's try another example. So let's say if y is equal to x squared ln x. Go ahead and find the differential. So the derivative of y is 1 times dy, which is simply dy. On the right side, we need to use the product rule. So f is x squared, g is going to be ln x, f prime is the derivative of x squared, which is 2x, and g prime, which is the derivative of ln x, that's 1 over x. So whenever you need to use the product rule, it's going to be f prime g plus f g prime. So the derivative of the first part, x squared, is 2x. That's f prime times g, which is ln x, plus f, which is x squared times g prime, which is 1 over x. And then whenever you differentiate an x variable, add a dx to it. So I'm just going to put it on the outside of everything in terms of x. So then this is the answer. Now we just got to simplify it. So dy is going to be 2x ln x. We can cancel an x variable, so plus x times dx. Let's try another example. Let's say if the volume of a sphere is 4/3 pi r cubed. Find the differential of the function. So the derivative of v is 1 times dv, and the derivative of r cubed is 3r squared times dr. So we can cancel 3 if we want. So dv is equal to 4 pi r squared dr. So this is the answer. Now keep in mind, another way in which you can get the answer is you can differentiate the function with respect to r. The derivative of v with respect to r is 1 times dv dr. the derivative of r cubed with respect to r is 3r squared times dr over dr, which cancels. The 3's cancel as well. So then you can see that dv over dr is equal to 4 pi r squared. And if you multiply both sides by dr, you're going to get the differential function dv. So dv is equal to 4 pi r squared times dr. So you can get the same equation using both techniques. Now let's try another problem. So let's say if y is equal to x cubed plus 6x, and this time we're given an x value and also the value of dx. So how can we find the differential dy? So dy, it's going to be the derivative of x cubed plus 6x, which is 3x squared plus 6, times dx. Now, if you want to prove that, you know that f of x is equal to x cubed plus 6x, because f of x is y, and f prime of x is equal to 3x squared plus 6. Earlier in this video, we said that dy is equal to f prime of x times dx. So if you replace f prime of x with 3x squared plus 6, you're going to get the function that we have on the left. So you can do it that way too if you want. So now let's calculate dy. So x is 2, so this is going to be 3 times 2 squared plus 6, and dx is 1/3. So let's replace dx with that. 2 squared is 4 times 3 is 12, and 12 plus 6 is 18. So 18 divided by 3, which is 18 times 1/3, that's 6. So dy is equal to 6. Let's try another example. Let's say if y is x to the 4th minus 8x plus 2, and x is 3, and dx is 0.1. Find dy and go ahead and evaluate it. Feel free to work on this example and see if you'll get the right answer. So dy is going to be 4x cubed minus 8, and the derivative of the constant 2 is 0, and then times dx. So now let's plug in the values. So x is equal to 3, and dx is 0.1. 3 to the 3rd power, 3 times 3 times 3 is 27. 4 times 27, that's 27 is 20 plus 7. 4 times 20 is 80. 4 times 7 is 28. So if you add them, you're going to get 108. 108 minus 8 is 100. And 100 times 0.1 is 10. So therefore, dy is equal to 10 when x is 3 and dx is 0.1. Now let's say if we have another similar problem. Let's say if we're given the function y is equal to x cubed, and the x value is 1, and instead of given dx, we're given delta x, and let's say it's 0.1. Let's calculate dy, which we did in the last example, but also delta y. How can we find these two variables? So to find dy, we know it's going to be the derivative of x cubed, which is 3x squared times dx. And remember, delta x is equal to dx. So to find dy, let's plug in 1. It's going to be 3 times 1 squared times dx, which is delta x, that's 0.1. So 3 times 0.1 is 0.3. So dy is 0.3. Now how can we calculate delta y? So delta y is basically y2 minus y1. It's the change in the y values of the tangent line. Well, not the tangent line, take that back. is the change in the y values of the function f of x. dy is the change in the y values for the tangent line function. y2 is f of x plus delta x, and y1 is simply f of x. X is 1, delta x is 0.1, so delta y is f of 1.1 minus f of 1. So what is f of 1.1? This is going to be 1.1 to the third power minus 1 to the third. 1.1 raised to the third power is about 1.331 minus 1. This is going to be 0.331. So as you can see, delta y, which is 0.331, is very close to dy. The reason being is the change in x is very small. If the change in x was larger, these two won't be so close. So let's try the same problem, but when delta x is larger. Let's say delta x is 0.5 instead of 0.1. So dy is still going to be 3x squared dx, which is 3 times 1 squared times 0.5. Half of 3 is 1.5, so that's the new dy value. Now delta y, which we said it was y2 minus y1, which is f of x plus delta x minus f of x. And x is still 1, but delta x is now 0.5. So delta y is f of 1.5 minus f of 1. So that's 1.5 to the third power minus 1 to the third power. So 1.5 to the third power is about 3.375 minus 1. So delta y is equal to 2.375. So notice that these two values are not that close because delta x is large. So as you increase delta x, dy and delta y, they deviate from each other. But when delta x is small, dy is approximately equal to delta y. So let's understand it from a graphical perspective. Let's graph x cubed. So x cubed is a function that looks something like this. And let's say this is an x value of 1. So here is the tangent line function. Now let's say this is 1. Let's say this is 1.1. And over here, let's say this is 1.5. So at 1.1, delta y and dy does not vary much. So this is delta x. It's the difference between 1 and 1.1. Delta x was 0.1 in the beginning of the problem. So that's delta x, which is also dx. dy is the change in the y value of the tangent line function. So that's dy. Delta y is the change in the y value of the function f of x, where dy is the change in the y value of the tangent line function. So as you can see, when delta x is small, delta y and dy are approximately equal to each other. Now what about when delta x is significantly larger? So let's say delta x this time is not 0.1, but it's 0.5. So delta x is the same as dx. So this time dy is going to be significantly larger, as we can see. But so is delta y. Now let's see if I can expand the graph. So let's continue this function. Let's say it continues to increase. So delta y is significantly larger than dy as delta x increases. As you move away from the point where the tangent line intersects the function, so basically as delta x increases, delta y and dy, they diverge from each other. But as delta x decreases, as you get closer to the point of intersection, delta y is approximately equal to dy. Now let's try one more problem. Let's say if y is equal to x cubed minus 5x plus 1 when x is 2 and when delta x is 0.1. Go ahead and calculate dy and delta y. So the derivative, or the differential of y, is going to be dy. The derivative of x cubed is 3x squared. The derivative of 5x is 5, and for the constant 1 is 0 times dx. So let's find dy first. So x is 2 and dx is 0.1. 2 squared is 4 times 3 is 12, and 12 minus 5 is 7. 7 times 0.1 is 0.7. So dy is 0.7. So now that we have the value of dy, let's calculate delta y. So delta y is y2 minus y1, which is f of x plus delta x minus f of x. X is 2, delta x is 0.1. So basically this is going to be f of 2.1 minus f of 2. So let's calculate f of 2.1. So let's plug it into the original function. So that's going to be 2.1 to the third minus 5 times 2.1 plus 1. And then let's plug in 2. So it's going to be 2 cubed minus 5 times 2 plus 1. 2.1 to the third power is about 9.261. And 5 times 2.1 is 10.5 plus 1. 2 to the third is 8. 5 and 2 is 10, but it's negative times another negative, which is positive 10. And distribute this to plus 1, so it's negative 1. So 1 minus 1 is 0. So we have 9.261 minus 8 plus 10 minus 10.5. 9.261 minus 8 is 1.261. And 10 minus 0.5, 10 minus 10.5 is 0.5. And 1.261 minus 0.5, it's going to be 0.761. So delta y is not too far away from dy, since delta x is relatively small. So that is it for this video. Thanks for watching and have a great day.